All right. So in the last two videos, we have been discussing a very interesting problem. And in the last lecture, we in fact saw a solution which seemed to be correct methodologically, but yet it gave us a wrong solution. And we and I kept you there to think that why the solution that we did is wrong. And I hope that you would have given a stab at that and had already figured out what's wrong in that solution. Now, in this particular video, we are gonna make corrections to our solution and hopefully arrive at the right answer. All right. So if you recall from the last video, this is what, the probability that we had set out to calculate, the probability that TB lies in the range TA plus sigma from to TA plus sigma plus D sigma, because remember that this is indeed equal to the probability that W lies in the range sigma and sigma plus D sigma. And to recall, why is that important? Because to calculate the density function of W at W equal to sigma, all that we'll have to do is divide that probability by D sigma and take the limit D sigma tends to 0. Okay, so until now it all makes sense. It's all quite easy. And so this is where we resume from. So this is the probability that we want to calculate. And as we saw that, we'll have to use the marginalization trick. And in the marginalization trick, we have to use the integration instead of the summation, because we are dealing with TA, which is a continuous random variable, right? So this is what the formula in front of you. Now, an interesting thing to note over here is that this conditional probability is actually not uniform, okay? It's not the same for every alpha. It changes with alpha, okay? To see an example, consider, let's say your start is 7 a.m., your end is 10 a.m. So remember, the start and end are the limits, uh, between which A and B will arrive. Okay, they will not arrive outside this. Okay, and they arrive randomly in between, anywhere in between these two limits, and nothing outside, and they arrive independently of each other. So all of this we remember from the problems setup. Now let's say TA arrives somewhere in between 7:30 a.m. and 10 a.m. All right. Oh, sorry, A arrives at this time, so TA is actually equal to is a quantity lying in this range. Now, so let's say, for example, the weight is of 2.5 hours. Okay, so what does it mean that the weight is 2.5 hours? Or for example, suppose we want to calculate the probability or the density function for sigma equals to 2.5. So we know that if sigma is 2.5, then that means that B will have to arrive at TA plus sigma, okay, somewhere around that, right, for sigma to be 2.5. Okay, but note that this is actually not possible for TA to for the particular TA that we are talking about. Why? Because the thing is that if TA arrives in the range 7:30 a.m. and 10 a.m., then TB for sigma to be 2.5 hours, TB will have to be at least 10 a.m. So B have to arrive after 10 a.m. All right, which is impossible because B can at max arrive at 10 a.m. Right, and that means, okay, and that's why you can see that this probability, okay, in is actually changing with the time at which A is arriving. All right, the probability that B is going to arrive at sigma time after A, this probability changes with what your alpha is. Okay, it's not the same for all alphas. All right, and in fact one can show that for any given sigma, this conditional probability is the probability that we saw earlier, which is to say that the probability that TB lies in this range if your alpha plus sigma is less than E. All right. So as long as your alpha plus sigma is less than E, this conditional probability is exactly the thing that we saw before, right? Because in that situation, we can guarantee that the event that we are talking about, which is to say that TB lies in the range TA plus sigma and TA plus sigma plus D sigma, will actually be less than E. All right. So because of that, this works. But on the other hand, if alpha plus sigma becomes larger than E, in that case, this probability becomes 0, right? Because then there's no way that B can arrive, because B at max can arrive at E. All right. And for the weight to be sigma, given that your alpha has already overshooten E minus sigma, for the weight to be sigma, B will have to arrive after E, which is not possible. So this probability, this conditional probability, note the word conditional probability, is 0. Okay. And now, hopefully this, solves the mistake that we did earlier, because if you remember, our earlier in the last video, or in our earlier iteration of the solution, we assume that this probability is the uniform for all alphas. Okay, but this time now we have fixed this, right? So for alpha less than E minus sigma, we have some other probability. For alpha larger than E minus sigma, we have the conditional probability 0. Okay, so this is all, hopefully all the correction that we need. So let's so let's substitute in these values in the integration that we are looking for, right? Again, here I've not written all the steps, but what I've done over here is that I've broken down the probability into, so remember the earlier probability that we were looking for, this one right over here, I've broken down them into two integrations, right? So an integration going from S to E minus sigma, and the other integration going from E minus sigma to E. All right. Now remember that the second term, or the integration going from E minus sigma to E, is 0 because the conditional probability inside is 0, right? So all that we need to care about is the first term, because that's the thing that's potentially non-zero, right? And that's what's written in front of you. And the other part is 0, which is being written as 0 over here. And again, I've replaced that conditional probability with this probability, because that's what we have found out in just the definition that we saw right now. And now if you just do substitute in and now this is quite obvious that the probability that TB lies in this range is nothing but the width divided by E minus S, because TB is uniformly distributed. So this is what, and upon substituting in that, and doing the integration, that's what you'll get, which implies that your density function of W comes out to be this. Okay, so note the difference. So earlier, we had no dependence upon sigma. In fact, we claimed that your W itself is uniformly distributed, but this time around, that's not the case. Now we can clearly see that this depends upon sigma, right? Because this came out directly out of our integration. We did not really have to do anything. Okay, that's directly what our integration is giving us. Okay, so your density function indeed depends upon sigma. Now let's verify whether the solution that we can get a sanity check correct, because the sanity check that we are looking for is that this integration should give us 1, or the probability that W lies between 0 and E minus S should give us 1. So this is what we want to evaluate. Now this is actually nothing but the sum of these two quantities, right? The quantity that W equal to 0, the probability that W equal to the weight is 0, and the other thing where the probability that W lies between 0 and E minus S, excluding 0. So yes, you do all the things that you have been doing earlier. You solve the integration, you substitute in the limits, and then you evaluate the limit. So indeed, the sum that you'll get is 1, which is what we expected, and hence we are correct. Okay.